Okay, team. We are going to be talking about average velocity. So if a person is going from 0 to 5 meters per second, they're speeding up. Their velocity is not constant. So we want to know, on average, if you're the coach, how fast did this person go during their race? Okay. So whenever you calculate an average, you're talking about a time interval. Okay, there's a period of time over which you are going to calculate the average. Why do you need to do that? Clearly, if we just looked at position versus time graphs where the velocity was constant, straight line, that'd be pretty boring, right? So we're looking at position versus time graphs what you have is, looks like here, a concave down parabola and then a line and then a concave up parabola. Okay, so that means the speed is changing, right? Constant slope means the speed is constant. Whenever you have parabolas, it means the velocity is changing. The object is speeding up or slowing down because the environment is pushing on it. And so again, if you're the coach, you want to know, hey, on average, how fast did the person go in a specific time interval? So the time interval we care about here is from 0 to 10. And you can see that the slope, the distance is changing quickly here. And then when it starts to level off, it's not changing as quickly. Okay, so the person's going from fast to slow. Hopefully you can see that. If not, keep working on it and reach out to your classmates or to me. Okay, so there's an infinite number of speeds, from going really fast to, oh my God, I see a stop sign and I'm going to start to slow down. But we want to know, on average, how fast did the car go in this time interval? So please write this equation down or formula down. The bar means average. So this says the average velocity is equal to, delta means difference, kind of like when you're doing, exactly like when you're doing slope. It's going to be x at point B minus x at point A. That delta x here, which is the rise, over this time minus that time, delta t, which is the run. Okay, so the average velocity between 2 points is the slope, rise over run, of the line that connects point A to point B. Okay, and again, I know you may not have done tangent lines, but hopefully it kind of makes sense that it's going kind of fast at A and then it's slowing down. And if you average the slope, if you averaged all of these slopes as you go along this curve, on average, they would average out to this kind of magenta line. Okay, if you don't see that, hopefully you can trust the process and write down this formula and we will practice it. Okay, I'm going to geek out for a second. I kind of said this before, but I want to just really emphasize the point. What does average mean? It means this person is going from whatever speed they have here, say 20 meters per second to 0 meters per second. And there's an infinite number of speeds, right? Your speedometer is going to go through all of the numbers between 40 and 0. And would you want to average all of those numbers out? Absolutely not. So, hey, wouldn't it be easier if we could just take the slope of this line and that just took a whole bunch of averages? Okay, so pretty cool that's what that does. All right, so now we're going to do a practice problem. Please follow along. I know it's hard to copy this diagram to your paper. I promise you'll get paper copies in class, but let's practice this. We want to know what the average velocity of the object in the time period from 0 to 5 is. So again, we're always talking about a time period over which you're going to take the average. So I labeled the coordinates for you. The object starts 50 meters away from the origin. So the fan cart, like in our lab, is going backwards towards Miss Groppy, and it's going backwards. But since you're heading for the vertex, it is slowing down. So it has some speed here that you can imagine as the slope of this line. And then at 5 seconds, the slope is 0. The location isn't 0, it's at 20 meters, but since you're at the vertex, the instantaneous speed is 0 because you're going from backwards to forwards. So for a split second, your speed is 0. All right, so we want to calculate the average velocity. So we want to take the slope of the secant or connecting line, this orange line. Okay, so please don't, oops, I'm still in lines. So please don't label this M or slope. I want you in physics to tell me what it represents, and what it represents is V bar, or average velocity. That was my extra line there. So V bar is going to be x2 minus x1 over t2 minus t1, which is, be careful, don't do the first number you see minus the second number you see, or the bigger minus the smaller. It's always the later in time. So what happened later was 20 meters minus 50 meters over t2 was 5 seconds, and t1 was 0 seconds. So we have a minus 30 meters per second, sorry, minus 30 meters in 5 seconds, or minus 6 meters per second. Okay, and that should make sense. Please check your work, because this slope, this orange line, has a negative slope. And then it looks like I wrote a little note that this function that I made in Desmos, the initial velocity was minus 12, so they were going backwards at 12, and then they slowed down to 0. So that would be the same as if they traveled at a constant speed of minus 6. And hopefully that makes sense. Remember the rabbit and the hare worksheet. I could go really, really fast and then slow down, and that would be the same in terms of getting to the same spot at the same time if I just went backwards at a constant speed of 6. Okay, so far, average velocity, slope of the connecting point. I'm guessing that you're all strong at taking slopes. Hopefully we're just putting kind of some physics word to some math that you already know. All right, try this question. Which time period has the greatest average speed? And your options are 0 to 2, 2 to 5, and 5 to 7. So they're not even time intervals, but that's okay. You can still define an average. So I'm going to pause the video and connect the points with lines. That might help you pick the right answer. Okay, so I have drawn the connecting line for each segment. So hopefully you can visually see that and tell me which of those has the greatest average speed, because the orange and the purple have negative velocity. They're going backwards. That means ignore it. Ignore the minus sign. So what I'm trying to say is negative 20 is faster than positive 10, right? Because 20 just means I'm going backwards at 20. Negative 20 means I'm going backwards at 20. Ignore the negative sign. Which one has the greatest average speed? And hopefully you can see that the orange line is the steepest, so that means it's the greatest average speed. this should also make sense because if we haven't talked about this yet, we will talk about it a lot. The closer you are to the vertex, vertex means that's where it's turning around. Okay, so these two time intervals were averaging a bunch of speeds that were close to the vertex. This time interval was averaging a bunch of speeds that were farther from the vertex. So by definition, I'm putting in my average all of the bigger values. Okay, but you can also visually see that that orange line is steeper than the purple or the magenta. Okay, another practice problem on your own. Determine the average velocity of the object in the time period from 5 to 12. All right, hopefully you got that one right. So I drew the magenta line so you could visualize what we're doing. And then you take x2 minus x1 over t2 minus t1, and I got 2.40 meters per second. Okay, this question connects back to the fan cart lab that we did. We've got a red parabola connected with a blue parabola. And which of these parabolas indicates a greater magnitude of acceleration? So what you have is a cart that's going backwards, but the fan is on, slowing it down. So the object's going backwards, how we define that, maybe towards the backfield, but the fan is pointing towards the freshman hallway, so it is slowing down. But because the fan stays on, it doesn't just stop like your car. It then starts reversing direction and does start going forward. And then we change the fan again, and the fan slows it down again, and then it heads backwards faster and faster and faster. Okay, so I'm not sure if all that made sense, but see if you can remember for the lab. What we have here is what I'm calling a very extreme parabola, if you continued that red parabola, and a more wide or less extreme parabola. So which of these has a greater magnitude just means I don't care which way it's being pushed, which one's being pushed harder. Okay, hopefully you got that right. The correct answer is the red one, because you can see it turned around more quickly than the blue one did. Okay, so the more extreme the parabola, the quicker that fan cart is coming to rest, which is the vertex, and then being pushed in the other direction. Okay, test your understanding here. What determines which of the two runners will win win a race? I'll let you pause and read it if you need to pause to read it. And the correct answer is B. Because the person could walk really, 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 really slowly for a long time, right? And then goes like super fast because they save their energy through the finish line. Hopefully that extreme example will help you realize that that person is not going to win. By definition, the person who wins the race is the person with the greatest average velocity, because the definition of average velocity is delta x, which is the same for everybody, right? The displacement is from the starting point to the finish line over delta t, and the smaller delta t is to win the race, that's in the denominator, the bigger the average velocity. Okay, so it's all about average. It's not about how quickly you finish how fast you're going when you physically cross the finish line. Okay, and then a couple more slides. Thanks for your patience. The average velocity washes out all the information of how the object got from one position to another. There's an infinite number of ways to do that. So, for example, the last one we talked about, person could kind of meander their way, and then the last, 3 meters of the race, run like heck. That would be the same as if the person ran really fast and then like, man, I'm tired, and then walked the whole way. which would be the same as if the person, walk the rest of the way. If the person went at some average speed, right? So like if you know that, I hate to talk about tests, but like the test average was a certain number. If you had 1,000 people taking a test, there's lots of different individual scores that would still give you that average of whatever, an 85 on the test. Okay, so there's an infinite number of ways to get from initial to final for the same average. Okay, so here is an example of clearly B is just heading straight there. C is like staying, oops, I didn't hear that the starting noise went off, and then I run like heck. So each of these objects has the same average velocity because they got to the same place, same final place in the same amount of time. Okay, they all have the same average velocity. They got from 15 to 35 in very, very different ways. And you wouldn't know that if all you knew was the average. Okay, almost done. Which object traveled the least distance? So if you had an odometer, which one would have racked up the least amount on the odometer? It is a tie because B and C did not backtrack. They both actually traveled their odometer to read 20 meters. Because C's odometer did nothing for a while, but it still got to 20 meters. It just kind of ticked up faster in that time interval. But A traveled more than 20 meters because it backtracked, and D also traveled more than 20 meters because it backtracked. Okay, that was kind of a tricky thinking question. And we already answered that. Which object or objects backtracked? And which object took the least amount of time to get to the final position? That one is a smart butt question. They all took the same time, 70 seconds. All right. So some people were inefficient in backtracking or doing nothing, but in the end, like C, made up for it by going way faster, right? C had to travel really, really fast here. So it made up for it. So they all got to the finish line at 70 seconds. That was a smart butt question. And that is the end of the play posit. Thank you for listening, and I will see you in class.